record of Mare basalt 10017 and show you how they imply that the Moon had a core dynamo 3.6 billion years ago. The study of the magnetism of extraterrestrial bodies can give clues about their internal structure. The existence of a global magnetic field implies that there is a liquid core, and therefore that the body is differentiated, which has strong implications on its thermal history. For a long time, it was not known whether the Moon was just a cold pile of rubble or a differentiated body with a metallic core. The absence of a global lunar dipole field seemed to support the first hypothesis. But the discovery of basalt at the surface of the Moon showed that some melting did occur. And the discovery of crustal magnetic anomalies and that the lunar samples were magnetized seemed to support the hypothesis of an ancient lunar dynamo. However, 20 years of paleomagnetic analysis of lunar samples failed to demonstrate unambiguously that there was a core dynamo. You can see from this graph that there seems to be a spike in intensity between 3.9 and 3.6 billion years. The Earth's surface flux today is at about 50 microtesla. So one surprising thing with these values is that some samples seem to have recorded very strong magnetizations, which is difficult to understand because according to the scaling laws, this would imply enormous fields at the core mantle boundary. Actually, most of the values in this graph are suspect because due to problems in the methodology and technical limitations and limitation in analytical methods of the time, it was not possible to conclude whether these magnetizations are indeed core dynamos. So this has led to study different mechanisms to explain the magnetism of lunar samples. For instance, impacts are known to generate high fields or to amplify existing fields. For instance, you can see that magnetic anomalies have been identified at the antipodes of impact basins. In the recent years, there's been a growing evidence that the Moon is a differentiated body, with both laser ranging experiments and reanalysis of seismic data pointing towards the existence of a liquid core. So with the advancement of our understanding of rock magnetism and the progress of technology and new analytical methods, it is possible today to revisit lunar paleomagnetism. So with a critical review of the literature, Mike Fuller and Ben Weiss have been able to identify which samples are most likely to provide records of ancient lunar fields. The criteria that have been used to select the sample and that must be met in order to demonstrate the existence of a lunar dynamo are the following. The samples must not be shocked. They must have a stable magnetization that is stable in direction throughout the alternating field demagnetization. And there must be agreement between the mutually oriented subsamples. The magnetization must be consistent with a thermal-remanent magnetization and be distinct from other kinds of magnetization, such as shock-remanent magnetization, which would be recorded with an impact. And finally, the last criterion was about the cooling time scale of the sample that must be well constrained and slower than 1 hour, which is the maximum duration of transient fields generated by impacts. Another very important part of this work is to characterize the magnetic properties of lunar samples with the work of Sonia Tiku. So I invite you to go and see her poster. Her main finding is that the absence of a stable magnetization in some lunar samples does not rule out the existence of a dynamo at the time of their formation. The first sample that was studied within this framework was troctolite 76535 with the work of Ian Garrick Bethel, who showed that the This rock recorded lunar dynamo 4.2 billion years ago. Sorry. The second rock to be studied was Mare basalt 10020, with the work of Erin Shea, who demonstrated that this Mare basalt has recorded a dynamo at 3.7 billion years ago. And I'm now moving on to the new results. So 10017 is fine-grained vesicular high potassium ilmenite basalt. It's the largest sample brought back with the Apollo 11 mission. It has a crystallization age of 3.6 billion years and cooling time teams did not carry out any study of mutually oriented subsamples. So this is the sample that we cut in 9 subsamples. 7 of them have been demagnetized with alternating fields. The results are presented with orthogonal projection plots. So the endpoint of the magnetization vector is projected on 2 orthogonal planes represented on the same figure. You can see the different sections with different slopes that correspond to different components of magnetization. You can see that there is a low crossivity component, which is easily removed, and a high crossivity component, which is very stable in direction throughout the demagnetization. And as you can see from these figures, the low crossivity component has different directions between the subsamples, whereas the high crossivity components have agreement in direction between the subsamples. For a few subsamples, we continue the demagnetization to much higher fields. This is one example of a sample that we demagnetized up to 290 millitesla, which is the maximum that our instruments can reach. And you can see that even after this very high field demagnetization, there is still magnetization that is in the same direction and is well above the detection limit of the instruments. This equal area plot summarizes our results. You can see that the low crossivity components are scattered in direction, which is typical of contamination by artificial fields, which could have happened during the transportation of the samples or maybe during the cutting, whereas the high crossivity components are clustered within 25 degrees, which shows the good agreement in direction for these samples. We then try to compare this magnetization with, to identify the kind of magnetization that happened. We apply a laboratory field and compare the demagnetization. You can see that the NRM, the natural remnant magnetization in red, most resembles what we call anisteritic remnant magnetization, which is an analog of thermal remnant magnetization, and is very different from IRM, which is what we would observe if the sample had been remagnetized, for instance, by being submitted to a strong field. One of the major headaches of paleomagneticists is to determine the paleointensities of samples, and not only for extraterrestrial magnetism. Ideally, for thermal remnant magnetization, the best way to recover the paleointensity would be to heat the samples. Unfortunately, this most often causes changes in the magnetic mineralogy. So we do have some methods to estimate the intensity of the fields that samples recorded, but these have very high uncertainties, up to a factor of 3 to 5, due to calibration factors that are different from between samples and not easily determined. So for 2 of the subsamples of 10017, we obtained paleointensities of 60 and 80 microtesla, which gives a very conservative minimum value of 12 microtesla for the recorded field. We also tried to evaluate how well this sample can record fields, and you can see from this figure that even samples about 1/10 of the inferred paleointensity can be reproduced by these samples, which shows that it's a good magnetic recorder. So As I told you, most values in this graph are suspect, so we can just forget about all of them and only keep the most recent studies. And this is the picture we get. We have those three samples that show the existence of a lunar dynamo with intensities that are in agreement with the theoretical limit, which is the maximum field that could have been generated by the moon according to the dynamo scaling laws. So the sample 10017 extends the lifetime of dynamo by 100 million years. So this is important because this becomes even clearer that it's not possible to have sustained a thermal convection-driven dynamo for so long, because the heat flux is unlikely to have been sufficient to generate such a dynamo after 4.1 billion years. And it nicely supports the hypothesis of an unconventional dynamo, like a mechanical stirring-driven dynamo. You can see from these models that such a dynamo could have lasted up to 3.5 billion years ago, and such a mechanical stirring-driven dynamo could have been initiated by orbital transition or impacts. So there are a few things remain to be done to strengthen the conclusions of this work with pressure experiments to investigate the shock remnant magnetization of this rock, and the thermal chronology to constrain its thermal history. And I'm also working on a project to demagnetize the rocks in controlled atmosphere to be able to obtain reliable paleointensities, which would have very strong implications on the core dynamo models. So I'd like to thank NLSI for funding and JSC and CAPTEM for allocating the samples. Thanks.
Thank you. I believe in your group there was another, I think it was at LPSC last year or the year before, there was another sample from about 3.2, 3.3, 3.4 billion years ago that you looked at. There was a suggestion there might be a field at that time. Did that not work out?
Well, I just started working recently, but I don't know about such a young sample, not at 3.2.
I'm sorry. Yeah, I believe this was well. I'd have to look at my notes. It was a student working in the Ben Weiss group, and they were looking at a very young.
Oh.
Oh.
You want to say something?
Yeah.
Yeah, so what we found consistently with the Apollo 15 rocks, which are around 3.3 and 3.4 billion years old, is due to the grain size of the iron particles. They're very big, so these multi-domain iron particles don't actually hold magnetization very well. So what we found is whenever we investigated more subsamples and tested for unidirectionality, we are not seeing, like they're basically poor magnetic recorders. So that preliminary result is a bit unreliable right now.
Okay.
Any other questions? Back to questions about? I have one actually. So the theoretical maximum line that you drew in the theoretical limit right here, is that from a convection-driven dynamo then, or?
I don't know exactly what model what scaling law they use for this, but I don't think it's limited to convection-driven dynamo.
Is that from the Dwyer?
I think so.